Okay, first question. Should I do these questions as well? Okay. So suppose F is a curl field, which of the following is true? What do you think? First, second, third, or fourth? First one. Why? If F is a curl field, then its divergence is 0. Is that so? Because if the divergence is 0, then F is a curl field. We know. So if the divergence is 0, then this integral must be 0 for any v. Okay. How about the second one? We cannot say anything on the second one, I think. But third one is always 0. If you give me a curl field, its flux through any closed surface S is always 0. Okay. And fourth one, F is a curl field, but I am computing curl of F, so it doesn't make sense. Okay. So the first one and the last one. First one is coming from what we just discussed, and the third one is coming from one of the results that we already have. Like you give me a curl field, and its flux through any closed surface S must be equal to 0. Okay, which of the following are not identities of vector calculus? So these were like some of the things that I was discussing. So the divergence of a curl field is 0, or the curl of a divergence field is 0. What is true? I think this is true. We discussed. If you give me a curl field, its divergence is 0. And if the divergence of the vector field is 0, then the vector field is curl field. Okay, yeah. Divergence of gradient is 0. I don't think so. Curl of curl is 0. I don't think. Curl of gradient is 0. The curl of a gradient field is always 0. These are two things that we just discussed in this section, which is 20.3, I think. Yeah. How about this one? Suppose C1 and C2 are two curves in three-dimensional space. C1 is in the z is equal to 0 plane, and C2 is equal z is equal to 1 plane. Like z is equal to 0 is something here, a curve, and there's a curve here at z is equal to 1. Both have counterclockwise orientation, which follows from Stokes theorem. Stokes theorem, if f is a surface spanning between the two. Because we have, I think, done this thing. And this result is same as, what do you think? Which one is true? Is it this one? The line integral around C1 should be same as line integral around C2. Yeah, we proved this thing. And how about this one? Is this true? But they are going in opposite direction. So counterclockwise. Hmm. Actually, all of these statements are okay, except I don't think so that the last one is true, because we cannot say this is true when the flux of this one through the surface S should be equal to 0, like F dot dA is 0, then we can say this thing. But out of these three, one of them is true, because select one. Yeah, select one. So out of these three, one is only true, and that depends on what is the orientation. We know that if this orientation is counterclockwise C1, the orientation on this one would be counterclockwise on C2. But C2 is clockwise, so maybe let me call that curve negative C2. So the flux through S should be equal to C1 plus negative C2. So if you apply negative here, this sign becomes negative, so this third is obviously not true. So C1 is flux plus C2. The first one seems to be true here. Okay, it's all about the orientation. Yeah. Yeah, so counterclockwise is the orientation of curves C1 and C2. But if you are applying exactly the result that we discussed, the direction or the orientation is coming from right hand rule on the boundaries. I can show you the result, I think, that we discussed. What section was that? Stokes theorem? Mm-hmm. 20.1. I don't remember where was that. Mm-hmm. So it should be something here. Yeah, this example. So we are saying that this statement is true. This is Stokes theorem. This guy is Stokes theorem, but this right hand side is 0 because of some reason that we proved. I think the curl is 0 because of that. Then this integral C is this boundary, this one and this one, can be decomposed into C1 and negative C2. Why negative C2? Because C1 is coming from the orientation of normal pointing outward. And if I draw a normal that points outward, this is the right hand rule. So this curve has orientation which is clockwise. That's why this guy is equal to this one plus negative C2. So if you remove this negative sign, this becomes negative, and then you have integral over C2. That's why I'm saying that this sign must be negative over there. Okay, so let's not waste time on these questions. You mean in the question they are saying that they go counterclockwise? But the orientation on the boundary gives us counterclockwise on one of the curves. Yeah. So C1 and C2 are both counterclockwise. But when you apply a theorem, the orientation of C1 is same as counterclockwise that we are given according to theorem. But C2 is counterclockwise. We do not get exactly same C2 if we apply the theorem. If you are applying theorem, we get negative C2. So theorem gives negative C2, but we are interested in this counterclockwise orientation. That's why whenever you see C2 here, it means this is counterclockwise. Whenever you see C1 here, it means it is counterclockwise. But theorem will give us negative C2 because of these orientation on the surfaces. So I think if this is negative, if this is negative on this side, if you take it on the right hand side, this becomes positive. So A seems to be correct, the first one. Yeah, but you cannot do that. If you take C1, which is in the Z is equal to 0 plane, you draw a normal here that goes out, the orientation gives you exactly this counterclockwise. So C1 should be positive. Yeah, because this outward normal on the surface gives us the same orientation of C1. Sorry, which one is counterclockwise? Is it this one? I have not drawn this correctly, that's a problem. That's happening because of that. Okay, let me do this thing. This is the front. So this guy is at the front. This is outward normal. This is the orientation. So this is the orientation which is counterclockwise on C1. It is explicitly mentioned here. C1 is in the z is equal to 0 plane. C2 is in the z is equal to 1 plane. So this is z is equal to 1. This is C2. If I draw a normal here, so by right hand rule, I get this one. So I get this orientation on C2. Okay. So that orientation is clockwise. So I am going to name this one, this curve C tilde 1 and C tilde 2. Here the orientation is counterclockwise, here the orientation is clockwise, but this is equal to negative C2, but this guy is exactly equal to C1. Yeah. So when you see C1 or C2, they are counterclockwise, but theorem and its orientation gives us counterclockwise and then clockwise. If you convert clockwise to counterclockwise, there appears a negative sign. That's the whole reason, that you will see a negative sign, and because of the negative sign, the first one seems to be true. Okay. Okay, this question will not be on exam. If it is on exam, you will get full marks. So leave it. Yeah, I think sorry. Yeah. Okay, this is a vector field is given to me, and C is the circle of radius 2 in the z is equal to 3 plane, centered at 1 comma 2 comma 3 with counterclockwise orientation. Find this. What should I do? Can I use any theorem or? So point is centered at 1 comma 2 comma 3. So x is 1, y is 2, z is 3. So maybe there's a point here which is in the plane z is equal to 3, and C is a circle of radius 2. It means something like this, but it is in that plane. Yeah, okay. With counterclockwise, so it's this one. Compute this. So we can explicitly compute this by using what do we say, parameterization and all the other things that we have done. But can we apply any result like maybe divergence theorem, Stokes theorem, or maybe Green's theorem, or something else? What do you think? Line integral can be computed by using what do you think? I think this is Stokes theorem, if we can apply. I don't want to make it complicated, so let's see. What does Stokes theorem say? Line integral is equal to the surface integral for the curl of vector field f. Okay, this is a Stokes theorem. Why am I using that? I can compute this guy explicitly, but that would be too much. You will be applying a Stokes theorem and divergence theorem for a couple of questions there. So like be prepared for that. Okay, so surface S, this line integral is simply integral on this boundary, and the surface S, this whole surface, which is this whole disk. I'm going to compute curl of the vector field F, and then I need to write what is dA. So dA is the area vector that is coming from right hand rule. I think it should be, if you apply right hand rule, the normal points in this direction, which you can see is exactly k hat. So it should be k hat dA. Agree? What is the curl of the vector field F, which is given by this one? You can compute its curl easily. You write I, j, and k, and partial by partial x, partial by partial y, partial by partial z. The x component is x minus y, the y component is 0, that's a good thing, and z component is y minus x. The curl of this vector field that you will get once you compute this determinant is, I have written that thing to be I plus j plus k, like 1 I hat plus 1 j hat plus 1 k hat. You compute that determinant, you will exactly get that thing. So you apply Stokes theorem, you compute the curl of vector field. Now you just integrate over this surface. I think this one is really simple now, because if I take this dot product, I will exactly get 1. Now you know what is this integral? Area of circle with radius 2 pi. So it's pi r square pi 2 square, which is 4 pi. That's it. So any vector field is given, we are interested in computing the line integral, we can apply Stokes theorem, as well as the boundary is nice, we can do that, and maybe in some problems it will be explicitly mentioned to apply Stokes theorem. For the same curve, suppose instead we consider this vector field. Now you compute this. So the geometry is same, the circle is same, counterclockwise orientation is same, just we are given a different vector field. So what is different here? And the different thing is you need to compute the curl of vector field G. So let me write it, curl of G, and whatever you get, you just use it here. Instead of curl of F, we will be having curl of G. You take the dot product and finally you will get something. So I'm only writing what should be the curl. So the curl of this vector field is 0. Okay. Once you compute, I have solutions here, it's 0, but you can verify. So the line integral should also be equal to 0, because this 0 vector is simply 0 I hat plus 0 j hat plus 0 k hat. If you write it here, take the dot product, you get 0, you integrate 0, you get 0. Okay? Questions? Now the next question is, suppose S is the cylinder with outward orientation, and this is cylinder of radius 1 around the z axis between z is equal to 1 and z is equal to 2. If F is this vector field, what is this flux of the vector field F through the surface S? Okay, so it's a cylinder around z axis, radius 1, so maybe between z is equal to 1 and z is equal to 2. So I think this one is the x, y, and z. Between z is equal to 1 and 2. Okay, so it shouldn't be like that. This point is z is equal to 1, this one is z is equal to 2. Okay, can we apply any theorem? We are interested in computing the flux of this vector field F through the surface S given by this cylinder. There is an explicit formula to compute this thing, and the second thing is we can also apply one of the results that we discussed. But that's, I think we can apply divergence theorem when we have a closed surface. We know that if you have a closed surface, the flux on the boundary is same as you compute the volume integral for the whole interior region, but this surface is not closed. Is it closed? It's not given, so we can assume. But how can we apply Stokes theorem here? We can apply Stokes theorem. We know that this flux is same as the line integral on the boundary. Yeah, we can apply Stokes theorem, it is explicitly given to us. So what is the boundary? The boundary is C. So let me call this guy C1 and let me call this guy C2 with counterclockwise orientation. So this will give me C1 F dot dr plus negative C2 F dot dr. Now you can ask me why I wrote negative C2 here. Why not C2? I am defining C1 and C2 to be curves with counterclockwise orientation. Those are my curves. I have written there counterclockwise. But the theorem says the boundary should be decided according to the orientation given by the surface. That's the main thing. If you use orientation of this surface, this one will give you counterclockwise, that's why I written C2, C1, and here it gives me clockwise orientation. So this curve with maybe this red line is negative C2, not C2. So this is the main reason. We have C1 and negative C2. If I am able to compute these two line integrals, this will give me the flux of vector field F through the surface S, which is given by this cylinder. How to do this thing? We can go to maybe back to chapter 18 and we know how to do these things. First of all, we need to define what is R of t for C1. C1 is a circle centered at origin, and the equation for that circle is going to be, now the parametric equations are going to be sine hat, sine t, is it sine t? No, cosine t, I hat plus sine t, j hat plus k hat. Why I have written k hat? Say it again. Z is 1. Yeah, okay. So now you know very well you need to compute R prime of t, which is negative sine t I hat plus cosine t j hat plus 0 k hat, because this is coefficient 1. If you differentiate, you get 0. And now along C1 we compute line integral by using this formula, R prime of t dt. So it's 0 to 2 pi, because that's a complete circle, f of r of t. It means in this vector field I replace everything with the parameterization. So if I use the exact notation given here, then y is equal to sine t, so negative sine t, and x is equal to cosine t, and z is equal to 1. So this is natural log of 1 dotted with r prime of t, which is negative sine t cosine t and 0 dt. Are you getting this notation? So instead of ijk, I am using this vector form, the 3 tuple form, and this one is r prime of t dt. If you take the dot product, then you get negative sine square t plus cosine square t, and then third term is 0 dt. I am not going to evaluate this thing for now. Then you can explicitly do what is this guy. For this one, you start with r of t to be, what do you think? It is cosine t, sine t, and 2k. Agree? Because this circle is in the plane z is equal to 2, that's why the value of z is equal to 2. And if you believe me, this whole thing will give you same expression. I have computed the line integral around C2. You can explicitly write this thing line integral around C1 and minus around C2. And since both of these expressions are exactly same, this is going to be 0. Okay, so we only applied Stokes theorem in the very first equation, which gives us the curve C, which is the boundary. The boundary can be decomposed into C1 and negative C2, and negative can be just written here like negative integral over C2. If you compute C1 and C2, they both are equal, hence this thing should be equal to 0. Yeah.
So to do the divergence one, like the question has to explicitly say it's closed, or we can't
But if it is not explicitly given, you cannot assume. Yeah. Yeah. And most of the times it should be mentioned that it is open cylinder or closed cylinder with the top and bottom, but it's not mentioned here. We cannot do this. Yeah. Okay, good to go. This is a nice question where we applied Stokes theorem. Next, here we are explicitly applying divergence theorem, and divergence theorem is like really simple. It's just you are computing a triple integral. So suppose f is this vector field, you can see the vector field is nice enough. It is like there is no points where the vector field is not defined. S is a sphere of radius 2, closed. A sphere is closed, radius 2, with outward orientation. That's the most important thing. We need to compute this guy, and we are going to apply divergence theorem. Divergence theorem says that the outward flux of this vector field through the boundary is same as you integrate the divergence of f over whole region W, which is inside the sphere, inside in the boundary. So I can compute the divergence of vector field f. Divergence of f is you partially differentiate the first component with respect to x, you will get 3. Second component with respect to y, you will get 2. Third component with respect to z, you will get 4. This is 9. Divergence is simple. I am not going to write everything like maybe if this number is not 9, this number is a function of x, y, z, then computing this integral is really sometimes difficult. And I would suggest you, if instead of 9 you have 9z, 9x square plus y square, anything, better to convert this into spherical coordinates, because it is a sphere, the region is spherical, convert spherical coordinates, then integrate. But I am not going to do this. And you know what is the integral? What is the integral of this one? Volume of sphere with radius 2. So it's I think 4/3 pi r cubed. That's it. Okay, very simple. Similarly, in B, I am going to apply divergence theorem again. First of all, I am going to compute what is the divergence of vector field F, which is 3x square plus 3y square plus 3z square, and I can maybe make it look nice by writing it in this way. Okay. So this flux through the boundary is same as you integrate the divergence of the vector field over whole W. So W3 what should I do? Spherical, no cylindrical, no Cartesian. This is again already Cartesian. So spherical totally makes sense. So triple integral, changing the integrand gives me 3 rho square. So you need to change the integrand, the limits, and the volume element. 3 things. The first one is done. What is the volume element? dV in spherical coordinates. Rho square. D rho, d phi, d theta. So many of you wrote rho in your exam 4 instead of rho square in the volume element. Okay, so be careful. There are only 3 coordinate systems. You should know volume elements in all these 3. Cartesian is simple, then you have rest 2. And then the limits are, the rho is, since the radius is 1, so it should be 0 to 1. And this is whole sphere, so phi should be 0 to pi, and this one should be 0 to 2 pi. And this guy will be 3 rho to the 4. I think I'm not going to do this. You just need to integrate each component, and you will get 12 pi or 5. So you integrate rho, then you integrate function of phi, which is sine phi, then you do theta. That's it. Good. So question 5. F is a curl field. Suppose we only know its first 2 components. What could the k component be? This is a good thing. So if you give me a curl field, we know that the divergence of curl field is always 0. I'm going to use this result to find out what should third component be. Okay, so this guy is F1, this guy is F2, and this guy is F3, which is not given to us. So divergence of this vector field is you differentiate F1 partially with respect to x, F2 partially with respect to y, F3 partially with respect to z. The derivative of F1 is y, F2 is z, this thing is 0. What should I do here to find what should be F3? Yeah, very good. So partial F3 by partial z is negative y, negative z. Next, integrate with respect to z gives me negative yz, negative z square over 2 plus, don't worry about that, right, c, that's it. Yeah, it should be a function of x and y, then you need to evaluate what should that function be, but no need to worry about that. So negative yz negative z square over 2 plus c. So we can do that. If we are given that some vector field is a curl field, we can explicitly compute what should the third component be if any component is missing. So what you can think of now, what this question tells basically, from exam point of view, you can get maybe one of the questions that looks like this. So what would be the difference? The components would be different. Okay, this can be maybe you will be asked to find maybe the first component or the second component or the third component. Okay, so mock final will maybe help you around 60% for your exam, and remaining percentage should be you review lecture notes, try to understand the things. Okay, what should I do here? This might be a little bit interesting because f is a gradient field. Then the result says, one of the results, if f is a gradient field, then curl of this vector field f should be equal to 0. Now this is the vector field, this guy is f1, this guy is f2, this guy is f3. The good thing is the third component is 0, so I can find its curl explicitly by using the simplest formula, but like if I don't want to do that, then what should I do? Okay, so let's do this thing. Curl of f is I j k partial by partial x partial by partial y partial by partial z, and I'm writing here f1 and here x over y and here 0. So if I ignore this row, this column, then the determinant gives me 0 minus 0 I hat, okay, minus I remove this one, then I differentiate with respect to x0 minus partial f1 by partial z j hat plus, now I remove this one, if I differentiate with respect to x, this is 1 over y minus partial f1 by partial y is equal to 0. Okay, 0 is a vector. So this is partial f1 by partial z j hat plus 1 over y minus partial f1 over partial y k hat is equal to 0. If it is a vector, it means its components are 0, partial f1 by partial z is equal to 0, and 1 over y minus partial f1 over partial y is equal to 0. These two informations I have. What should I do next? Like, first of all, they are equal to 0. If I explicitly look at this expression, then this expression says that I can do like partial f1 by partial y is 1 over y. If I integrate with respect to y, then f1 is natural log of y plus some constant. Now that constant can be a function of x, a function of y, or only function of x or z, for example, for now. And this says that whatever that f1 is, if you differentiate that with respect to z, it is 0. Okay, so f1 is basically a constant function of x only, not z, which is a function of x. So this function should explicitly be a function of x, but if you are not interested in any of these things, then f1 is natural log of y plus c. That's it. Natural log of y plus a constant. So to make your life easy, I'm doing one thing. I'm saying this equality says that this is a function of not z, but it can be a function of x and y. But already y is there and I have a constant, so this should be the right expression. Okay, without looking at others. Okay, next. Calculate the flux of this vector field through the plane with upward orientation in this pitch. Now it comes to apply some of the formulas. If you remember, we had a formula of computing the flux of a vector field F through some surface S, area element and S. It is exactly, you write F, take its dot product with something. What was that? Negative Fx I hat, negative Fy j hat, plus k hat if I am not wrong, and integrate it in the region with respect to area element, which is dx dy, something like that. Do you remember? You are given a surface by an equation which is z is equal to f of x comma y, and this is how we do this flux through this surface S. Okay, so what am I going to do is, this is f of x comma y, the right hand side only. If you compute fx, you get 2. If you compute fy, you get 1. So the region is, x is between 0 and 1, y is between 2 and 3. This is the region. The vector field is this one. So I am going to write vector field in the same notation, which is x plus y, y plus z, but I am going to replace z by 2x plus y minus 1, and then I have third component z, which is 2x plus y minus 1, dotted with negative fx, which is negative 2, negative fy, which is negative 1, and then k component is simply 1, dx dy. If you take dot product, so you just multiply x plus y with negative 2, y plus 2x plus y minus 1 with negative 1, and 2x plus y minus 1 with 1, and then you integrate with respect to x, and after that you integrate with respect to y. This is how we compute this flux through any surface S. Determine, or the surface is given by the equation z is equal to f of x comma y. Okay, good to go. I'm not going to solve it. So function can be anything. You need to know this formula. In the vector field f, you replace z by that function, and then you take the dot product with this vector given by negative fx, negative fy, and z component is plus 1, and you integrate in this xy region, and you also decide what should these limits be. If the limits are nicely given, then I think we are good to go. And for this question, can I apply divergence theorem? Yes or no? I am interested in computing the flux through the sphere of radius 1 without outward orientation of this vector field. The vector field is nice, the surface is nice. I am interested in what is the flux of this vector field through the surface. I can apply divergence theorem because the surface is closed, everything is good. So W is the region, the divergence of vector field F, and this is volume element. It remains to evaluate what is the divergence of vector field F. Can you tell me what is that? 0. Differentiate x with respect to x, you get 1. Y with respect to y, you get 1. Negative 2z with respect to z, you get negative 2. 0. 0. Sometimes maybe you get questions like this. But obviously it is not explicitly mentioned what to use, but you can think of the vector field is good, the surface is smooth, everything is good. you are computing the flux through a closed surface. So just you integrate the divergence over the whole region in 3 space.
How can you tell it's a closed surface?
It's a sphere of radius 1 closed. Okay. These are some other questions. Yeah. So the good thing is maybe next many questions will be from exam 1 to 4. So not exactly same questions, but the idea can be same. I think can you tell me which one of these are true? I think the first one is true. Second one is not true. Third one is not true. Fourth one is true. If V and W are parallel, then you have cosine theta, and they are parallel, theta is 0, cosine 0 is 1. Yeah. The directional derivative definition. I think the first one is okay. The second one as well. Let me know if I'm doing anything wrong here. Directional derivatives are only defined for differentiable functions. Not necessarily. The directional derivative in one direction may exist, and maybe in another direction it does not exist. It means the function is not differentiable. But it depends on what direction you are choosing. Yeah, so we cannot say it's true. If the directional derivative at p in the direction of u is 0, then the level set through p has a tangent in the u direction. What does that say? No, just leave it. I think it's not true. How about C? Select one only. Tell me which one is true. The second one. Because of this is just change in cylindrical coordinates. So the volume element is r, dr, d theta, dz. In this question, you need to compute cross product. You can do it. Part B, you need to compute the area of a rhombus given by these sides. And I think if one of the vectors is 1, 0, another vectors is 1, 1, how do you compute this area? Do you know any formula? Magnitude of the cross product, yeah. Because cross product is a vector which is orthogonal to this, and its magnitude is exactly, because rhombus is another name for parallelogram, but they are obviously different. In parallelogram, one side can be longer, another side can be shorter, but opposite sides are parallel. In rhombus, all the sides are equal in length and parallel. Since the angles are not right, so we cannot call it a square. Okay. And find the volume of P, where P is a parallelepiped with these sides, and I think you know the formula. You just compute the determinant of 1, 0, 0, 2, 1, 1, and 0, 2, 3. And if it is a negative number, you take its absolute value. It gives you the volume of parallelepiped in 3 space. Find a plane passing through these 3 points. You know what to do. Can you tell me like whether we can apply the slope in x direction, slope in y direction, and what was the formula? Z plus m x minus x0 plus n, something like this? Yeah. You choose x0, y0, z0 to be this point, then you find the slope in x direction and slope in y direction. When one thing is true, can you tell me what is that? there must be 2 points where x value is same. Those are P and R. They give you slope in y direction, and then choose 2 points where y value is same. Yes, no? Z is same, yeah. So you can find slope in x direction and slope in z direction, I think. No. If x value is same, this gives you slope in y direction, but since y values are not same, x same gives you z slope basically, and z same gives you x slope. Now you are not finding x and y slope, you are finding x and z slope. So you should do this thing. Y is equal to y0. You can do this thing.
So instead of doing like C0 minus C1 over X0 minus X1, it'd be Y0 over.
Yeah, you're right. So what is the difference? You are interchanging the role of y with the role of z. That's it. So z becomes y and y becomes z. That's it. Yeah.
What if like I swear I saw something like this in the notes. It was like we found a displacement vector like
You can do that. You can do that. I did not go for that, but you can do that. So if anyone wants to leave, you may, but maybe I will take 5 to 10 more minutes if you want to stay. So I think it's also a good point if you are given only 3 points, P, Q, and R, for example, P, Q, R, you find this vector and this vector, and then what was the formula for that? You find a vector which is orthogonal to these both vectors. It means their cross product. So now you know vector PQ, for example, you know vector PR, you take their cross product, it gives you a vector which is orthogonal to these. Let me call this vector to be vector n, and once you do this, it will give you a vector ABC, and you choose a point, then the equation of plane was is it this one, x minus x0, b y minus y0, c z minus z0 is equal to 0. Okay, so ABC is the vector which is coming from the cross product of these two vectors. It means it is orthogonal, and x0, y0, z0 is any point from these 3 points. You can choose any. Okay, so we have explicitly done these examples. You can see lecture notes, as well as you will find these examples in your exams from 1 to 4. How to integrate this one over the solid cylinder of radius 3 between z is equal to 0 and z is equal to 1. The question is, what coordinates should I use? Like, what coordinate system should I use to integrate this function? Cylindrical. Okay, the reason is the region is a solid cylinder of radius 3 between z is equal to 0 and z is equal to 1. So I'm going to integrate f, and there will be a volume element because this is going to be a triple integral over some region. Volume element is r dr d theta dz, and I need to convert the function into these cylindrical coordinates. I need to write the limits. Can you tell me what this function would be in cylindrical coordinates? So r square is defined to be x square plus y square, and z remains z, and r is between 0 and 3, That's the radius. Theta is 0 to 2 pi and z is between 0 and 1, and you can integrate this one easily. So depending on the geometry, you convert the problem into right coordinate system. Integration would be easy, I think. Okay, if I have final answer, it should be, yeah, it should be 45 pi, but you do this as well. Okay, next 11, find the gradient for each of these functions. You know how to compute the gradient. You partially differentiate with respect to x, with respect to y, with respect to z, and that's it. Yeah, it's going to be a vector, something I hat, something j hat, and something k hat. So yeah, this one is okay. This is also a scalar field given to us, and we are interested in computing its gradient. So again, it's simple. So I'm not doing this. But be careful, you need to apply quotient rule, chain rule. As I've seen many examples, like I think there was one question in exam 4. What was it? 2 sine square t. The derivative, many of you wrote 2 cosine square t. It's derivative simply. You are differentiating. But obviously it is wrong. You know that thing. You need to apply chain rule. Okay, I think this is the very last question. We are interested in what is the maximum value of this function. Can you tell me what should I do for this one? Like there are two things that I can do depending upon what is the geometry given to me. Geometry means the constraint that is given to me. If the constraint is exactly equality constraint, like equal sign, then I apply Lagrange multipliers. If the constraint is this inequality sign, then I apply both Lagrange multipliers and finding these critical points and just seeing, okay, which critical point gives me maximum or minimum value. So this is the key point. Since this is an equality constraint, so I'm doing this thing. First of all, I'm taking derivative with respect to x and derivative with respect to y and setting these both equal to 0. And finding the values of x and y where the partial derivatives become 0. Is it possible? Never, because partial derivative is 1 with respect to x. With respect to y, it's 2. Are they 0 at some points? No, never. They are never 0. So never. It means we cannot apply this what do we say, second derivative test and finding critical points, which one is maximum, which one is minimum, which one is saddle. We cannot do this thing. What I can do now is what we say Lagrange multipliers, and Lagrange multipliers are solve this system. This thing meant that I did not find any critical points or any max or min values inside the region. Now I'm looking at what happens on the boundary. Okay, how to compute these things? I think after this we are done, and let me do this thing. Gradient of f is partial derivative with respect to x, partial derivative with respect to y is equal to lambda, and then I'm computing partial derivative of g, and let me write g here. G of x comma y is equal to x square plus y minus 1 square is equal to 4, and partial derivative with respect to x is 2x, with respect to y is 2y minus 1, and I have x square plus y minus 1 square is equal to 4. So one of the equalities gives me 2x lambda is equal to 1 and 2y minus 1 lambda is equal to 2. So from here lambda is equal to 1 over 2x, and from here lambda is equal to 1 over y minus 1. If I equate these two things, I get y minus 1 is equal to 2x. So what I can do is, in this equation I can replace y minus 1 with 2x to get x square plus 2x square is equal to 4. So this is 5x square is equal to 4, x square is 4 over 5, x is plus minus 2 over root 5. So y is obviously plus minus 4 over root 5 plus 1. Okay, so the points are 2 over root 5 and 4 over root 5 plus 1, negative 2 over root 5, negative 4 over root 5 plus 1. Now see the function value at, let us call this point A, this point B, function value at A and function value at B to decide which one gives you maximum. I think A will give us maximum, implies max, and this one implies min. What we are interested in. What is the maximum value of f? So exactly evaluate what is the value when you evaluate the function at point A, and that value is 2 over root 5 plus x plus 2y 5 plus 2, which is okay. So let me know if you have any questions, and I will also be uploading this by tonight, this video.